Before the first atomic bomb was ever tested, the Manhattan Project scientists ran into a terrifying mathematical problem. Physicist Edward Teller calculated that the extreme heat of a nuclear explosion might be intense enough to ignite the nitrogen that makes up 78% of Earth's atmosphere. The project's chief calculator, Hans Bethe, ran the numbers repeatedly to check Teller's math. Bethe concluded that the chance of incinerating the entire planet in a giant fireball was, in his words, almost zero. But almost zero still meant there was a risk. Project leader J. Robert Oppenheimer ordered this apocalyptic calculation to be kept strictly secret from both the public and the government, fearing their funding would be cut if the truth got out. The team pushed the button anyway. The atmosphere didn't burn. While they successfully avoided setting the sky on fire, their gamble paved the way for an entirely different kind of global destruction. Today, the world is armed with over 12,500 nuclear weapons. To understand the true threat of that massive stockpile, we have to look past the blast itself and see how humanity accidentally engineered a freezing global death. The path to the atomic bomb began with a string of lucky accidents. In 1895, a German scientist named Wilhelm Röntgen noticed mysterious invisible rays leaking out of a black cardboard box and illuminating a chemical plate across his lab. To prove these new X-rays existed, Röntgen placed his wife's hand in the path of the beam, capturing this exact photograph of her skeletal structure and wedding ring. Shortly after, Henri Becquerel tried to prove that sunlight could make uranium emit similar rays. When a streak of cloudy weather ruined his experiment, he locked his uranium in a dark drawer with some photographic plates. Checking them later, he found the plates were fully exposed. The uranium was generating its own spontaneous radiation. Albert Einstein then proved that mass could turn into pure energy with his famous equation, E equals mc squared. Soon after, James Chadwick discovered the neutron, a subatomic particle with no electrical charge, allowing it to bypass electromagnetic repulsion and strike an atom's nucleus directly. This animation illustrates the foundational physics of the bomb. When a single uranium atom is split by a neutron, it releases extra neutrons. Those newly freed particles then strike neighboring atoms in an exponentially growing, self-sustaining loop known as a chain reaction. In 1942, physicist Enrico Fermi proved this theoretical loop could be controlled and weaponized. He risked his life to build the world's first nuclear reactor in the basement of a Chicago university. Fermi proved the chain reaction worked on a small scale. Scaling up that microscopic physics resulted in a weapon capable of generating uncontrollable, concentrated destruction across entire cities. When a nuclear bomb detonates over a populated area, the immediate destruction is absolute. In this city cross-section, the blast generates immense heat, creating a firestorm. Superheated air from the explosion rises violently into the sky. Acting like a massive vacuum, it rapidly sucks in cold air, generating hurricane winds that drag debris directly into the inferno. Oppenheimer's original atomic bomb may not have ignited the entire atmosphere, but it successfully weaponized fire against specific targets. If those weapons are deployed at scale today, the resulting firestorms trigger a much colder global consequence. In 1983, an independent group of scientists, including astronomer Carl Sagan, published the TTAPS study. They shifted the scientific focus away from Teller's unlikely fear of fire and toward the highly probable reality of ice. Their calculations showed that if 5,000 nuclear weapons were detonated, the resulting firestorms would blast 1 billion tons of black soot and radioactive dust directly into the sky. Looking at this atmospheric cross-section reveals exactly why that soot is so dangerous. The debris is pushed 15 kilometers up, completely bypassing the lower weather systems and rain cycles. Once it reaches the high stratosphere, it becomes permanently trapped. As this dark cloud spreads across the globe, it blocks 70 to 90% of incoming sunlight. Within weeks, global average temperatures would plummet to -25 degrees Celsius, plunging the planet into a deep freeze for decades. You don't even need superpower arsenals to cause this. Scientist Alan Robach calculated that a regional conflict utilizing just a fraction of the global stockpile, like a war between India and Pakistan, would throw up enough soot to trigger this global freeze. The detonation is only the beginning of the catastrophe. The ensuing permanent darkness halts photosynthesis, causing the total collapse of the global food chain. Surviving a post-nuclear world requires massive infrastructural shifts. Humanity would have to rapidly relocate to deep underground civil shelters and rely entirely on artificial vertical farming. Our primary food source would likely be spirulina, a highly nutritious algae that requires very little light and space to grow. It's an extreme agricultural tactic, successfully used during Cuba's severe economic crisis in the 1990s. Remaining electronics would need to be shielded within days to survive the global electromagnetic pulses generated by the blasts. Massive medical stockpiles of potassium iodide tablets would be absolutely essential to stave off widespread radiation poisoning from compromised groundwater. Because the attacker will starve and freeze in the exact same nuclear winter as the nation they targeted, no one actually wins. The only real survival strategy is ensuring the button is never pressed in the first place.